Well, you can think of it like this. The power supply creates a pressure difference between its 2 points, and this difference forces electricity, or electrons if you like, to flow around the circuit. Think of the power supply as a pump connected to a loop of plumbing pipes. The pump does not create water. The water is already present in the pipe. It simply moves it. Similarly, the power supply does not create electrons. The electrons are already present in the wires and in the load. It simply moves them around. This pressure difference is known as the voltage or potential difference between the two ends, and it's denoted by V. It's measured in units of volts, and the symbol for that unit is also V. Now, we assume throughout that the conducting wires of the circuit are excellent conductors. In other words, their electrons are free to roam freely from one atom to the next. In the load, however, the story is different. There will be some resistance to the movement of electrons. This resistance is denoted by R, and it's measured in ohms. The symbol for that unit is omega, the capital omega letter in the Greek alphabet. Now, once the circuit is closed, current will flow. This current is denoted by I, and it measures the charge that flows through a unit cross-sectional area in each second. The unit for the measurement is ampere, and it's denoted by the letter A. Incidentally, volt, ampere, and ohm are named in honor of three physicists who worked in this area in the late 19th century. Now, in certain loads, the current that flows in the load is proportional to the voltage applied across it, and the proportionality constant is exactly the resistance R. In such loads, known as ohmic loads, we have a simple formula known as Ohm's law, and it says that the voltage is related to the current by this equation. Notice that not everything is ohmic. For example, the resistor in your toaster is ohmic, but an LED is not ohmic. Finally, I'd like to introduce one last equation, and it measures the rate at which a load consumes electricity. This rate is known as P and can be computed for any material, whether it's ohmic or not, by the product of the voltage times the current, and it's measured in watts. So let's take an example. Suppose you apply a voltage of 100 volts to a load, and the current that flows happen to be 10 amps. So the product is 1000 watt, or if you like, 1 kilowatt. This power is related to how much you are charged for electricity. If such a load, that is 1 kilowatt load, is used for 1 hour, it will consume 1 kilowatt hour. And in today's rate, it's about 10 cents per kilowatt hour. Let's take an example. In here, I have put a resistor across as a load, and so it is ohmic. Let's assume that our power supply supplies 3 volts, and this resistor is 10 kilo ohm. What will be the current that will flow in the circuit? The answer is 0.3 milliamp. Why? As you can see here, the voltage, this is Ohm's law, is Ri, so I is V over R. V is 3 volts, R is 10,000. That leads to 0.3 milliamp. Let's take an example that demonstrates Ohm's law. Suppose we have a power source supplying 3 volts, a load, an ohmic load, I put a resistor here, of 10 kilo ohms. How many amps will flow through the circuit? The answer is 0.3 milliamp. Why? Ohm's law says V is equal R times I, so I is V over R. 3 divided by 10,000 is 0.3 milliamp.